Okay, so let's go over the test. And then I would like to cover the carboxylic acid derivatives chapter. And then if we have time, the electrophilic aromatic substitution chapter. So I'm going to try to see if I can finish up those couple of chapters. So the multiple choice, any questions on the multiple choice? I think they were kind of, I mean, some people did not do very well on them, but at least the good side is on the final exam, you'll see the same ones. They'll just be scrambled, and I'll take, so each exam had like maybe 7 multiple choice questions. So because the final exam is going to be the same length as a regular exam, it'll only be an hour exam because I have to be able to grade it in time. So then what that translates to is I'll take like 3 questions out of each, 3 or 4 questions out of each exam 1 to exam 1, exam 2, exam 3, multiple choice questions, and then maybe come up with 1 more multiple choice question out of the material after exam number 3, and then I'll put all of those on the exam. So that's a third of the exam material will be the multiple choice. The other 2/3 will be the normal short answer, long answers. And will those be identical? No. I never give the same long answers, short answers, but they'll be kind of similar in the way that quizzes are similar to tests. So, I would expect that. Any questions on the multiple choice part? Because you'll see them, I mean, not all of them. And for as far as what'll show up on the final out of the multiple choice, I'm thinking to myself for the final that I'm trying to choose questions that sort of reflect things that you should leave the course knowing. If you've taken organic chemistry, you should have this still stuck in your head at 10 years after you've taken the course. I'm just sort of grasping at the possibilities, although I know you'll probably forget what you learned in this class, like sometimes a month after, or sometimes like a week after. But anyway, so the objective is, so I'm looking for questions out of the multiple choice that are like stuff that you should leave the class knowing. So it wouldn't be like nitpicky little questions. It would be like major questions. You do also have the 2 pages, both sides, officially allowed cheat sheet that you do get to come to the exam with. And if you were already doing your little 3x5 cards, I would just copy them and put them on a piece of paper so that you don't have to waste time, rewriting those all up from the beginning of the semester, because it takes a lot of time to write those up. So what I did for the reactions, I gave you the answers for what the reactions should have had for the answer. And the only, if it was off by a methyl group, you would have lost full credit. And the reason why you would have lost full credit is because as far as an organic chemist goes, for you to actually add on an extra methyl group, it actually involves very complicated synthesis. So that would not happen. So, if can you imagine somebody's developing a synthesis for a pharmaceutical development or something like that, and because they don't really know they're organic, even though they have an equation sheet, they're off by a methyl group, and then they make up this product that they're trying to make, and it turns out, no, it's not the product that you're trying to get to. It's off by a methyl group, and you have to do an entire different synthesis. So, that is completely wrong. The only thing I gave partial credit for on the equations are if you gave me an intermediate on the way to the product, or if you went like an oxidation that went too far or something like that, then I would have given you partial credit for that. Other than that, there were no other partial credit for the reaction. That's the way I always grade reactions. So this one was just there was not much. If you had the wrong thing in the wrong blank, you lost points. On this one, you can if I ask you an IR question, you can always say that it has a CH group, because all organic molecules have a CH group. So you could have given that. So every problem, you can always write down CH group, and the 2850 50 to 2960 for a CH group, and I would only give you the IR sheet that I gave you all semester long. It's not like I'm going to give you something different. And then you had to say, well, if you give this molecule and you tell me that you have an OH of a carboxylic acid, that would not be correct. Why not? There's no carboxylic acid here. You would not get a OH of a carboxylic acid. You would get an OH of an alcohol. So you had to say, here you would have had, I wrote it up here, OH of an alcohol, CO of an alcohol, but not like an OH of a carboxylic acid. That would be incorrect. I would have counted both this and this wrong, because you would not have, what?
Even though it's the same number?
The same number as in, I don't think it was the same number. I think that chart had a slightly different, the IR chart had a slightly different number for the carboxylic acid and the OH. Kind of similar, but not exactly the same. Acids here. So OH of a carboxylic acid and OH of an alcohol. OH of an alcohol says 3,400 to 3,500. 3,400 to 3,650 is the OH of an alcohol. The OH of a carboxylic acid says 2,500. OH of a carboxylic acid says 2,500 to 3,100. That's not the same number. So it would have been entirely wrong. Okay. So, and then on this molecule, I gave you a double bond, so you could have given me the double bond. And you had a hydrogen group hanging off of a double bond. So there was a stretch for a CH off of a double bond. So you could have given me that number. So, and you know, the reason why I gave you this simple IR table is so you can use the exact number that shows up on this IR table instead of, you know, trying to say, oh, the OH stretch is somewhere in the 3,000 region. You had the chart. So that was the point of having the chart. Okay, so the other version had a different molecule, but anyway. So the way I graded the NMR problem is this thing was very symmetrical molecule. So A and E gave the same chemical shift. B and D gave the same, can't see. A and E had the same chemical shift. B and D had the same chemical shift. And then C had a different chemical shift. So the integration would have been actually 6 for A and E together. Now, some of you actually wrote it out separately. I mostly gave people points for if you did that. You knew that there were at least 3 for each integration, although you treated it as if there were, like, you know, 6 peaks and 5 peaks instead of only having 3. But I anticipated that you would have 3 peaks. So I gave you 6 points. So I said 2 points, 2 points, 2 points. So if there was something wrong with your one of the 2 points, then you would have lost points on that. And then on the integration, all you had to do is just count the number of hydrogens. So 1 hydrogen, 4 hydrogen, 6 hydrogen. It was a little hard to figure out what some people were writing on their NMR data, because they had like numbers here, and then there was like this is this part of the molecule and another part of the paper, and it was hard to decipher what you meant, because, you know, you didn't actually identify, because I gave you letters. So I wrote on my answer that this is C, this is BD, and this is AE. So if you said C, BD, and AE, then you would have been perfectly correct. If you just gave me some peaks, but you didn't identify what the peaks were, that was kind of hard for me to decipher. A bad attempt is I looked at it and I couldn't figure out what you were doing, heads or tails. Made no sense to me, so I just said bad attempt -3. If you had something that I considered unrelated, it was just honestly, it was just a bunch of junk. You wrote something down, but I could tell you had no idea what you were doing, but you slapped something down on there, then you got -6. And then for the coupling equation, you had to come up with a number so that the coupling for the proton was the neighboring protons, not the protons directly attached to the same carbon. Yep. About the what? The question after the end of the reactions? What number? What page are we talking about? Page 4. This?
Yeah.
Yep, what about it?
Why would A be the most? Yeah.
I gave you a list. I gave you a list of most reactive carboxylic acid derivative to least reactive.
Why would that the least reactive one is A, and then
No, it says A for most reactive, C for least reactive. It says right on the question. A for most reactive, C for least. Well, let's look at the other form. I don't think I changed that between, I just changed the position of the atoms. I didn't change the question at all between different versions. And look at your version. A for most reactive, C for least reactive. And I bold and underlined it because sometimes people get that backwards if they're not sure.
Why is C not?
Because 2 of them had to be the same. Because carboxylic acid and esters had the same most reactive to least reactive. Carboxylic acids and esters are about the same. So I said that you should use the same letter for 2 of the functional groups. So you were supposed to use the same letter for 2 of the functional groups. So all I did between one form and the other is I didn't change this. I just changed which molecule showed up. Okay, any other questions about anything before I, okay, so we were on the NMR question. Okay, and the other form had a different molecule. So it did also have it also had a symmetrical molecule. It had a symmetrical molecule, but it had a different symmetrical molecule. So the one version had, so this one actually also had 3 peaks because you had this, and then you had the B that was the carbon, the hydrogen attached to the carbon. And then this was the C. The C was the OH hydrogen. So it also had 3 peaks. So 2 points, 2 points, 2 points. And then, you know, the integration, you would count the number of hydrogens and the N value. So for the N value on this version, make it a little bit larger. It's hard to see. Okay, so the N on this version was that C had neighbors on either side. It had 2 neighbors on the right and 2 neighbors, 2 neighbors on the left and 2 neighbors on the right. So it had 4 neighbors total. So C had N equals 4, which means that when you do the N plus 1 equation, you end up with 5. So this peak right here, this one would have been a quintet, 5 little peaks. So then the BD would have had this neighbor and then these 3 neighbors. Would have had this neighbor and these 3 neighbors, so a total of 4 neighbors. So then it would have had N is equal to 4, or the number of peaks is equal to 5. And then the last one over here only had 1 neighbor. You don't think this neighbor and then that over there is a neighbor because it's not next to it. The only thing that's next to it is just these 2. So it had N is equal to 2, and then you do 2 plus 1 and then you get 3. So that would have been one version. The other version had, so you did have an OH. Now the OH doesn't actually couple because it's an exchanging proton. I think I made a point of saying that a couple of times during the course of the discussion on the NMR. So this one doesn't couple. So even though it is there, it does not couple. So B only has these 2. B has these two sets of neighbors. So there's 3 on this side, there's 3 on this side. So B has 6 neighbors. So N is equal to 6 for B. N is equal to C, doesn't couple because it's an exchanging proton because it's OH. The B has 2 sets of neighbors, 3 on the right side, 3 on the left side. So then it has 6 neighbors, and 6 plus 1 gives you 7. And then AD has only the 1 neighbor. So then it's N is equal to 1, and 1 plus 1 is equal to 2. So once again, conveniently, I had 6 points, 2 points, 2 points, 2 points. And then once again, that attempt sort of looked like you know what you were doing. -6, it was unrelated. You know, I could tell you were just writing things down, but you had no idea what you were doing. -6 for that. And so it would have been 2 points, 2 points, 2 points, because conveniently I came up with a 6-point question so that it would work out. And then down here on the carbon NMR, these, and people got the coupling for the carbon back reversed with the coupling for the protons. So for the carbon, it's the protons that are actually attached to that carbon that gives you the number of neighbors. It's not the neighboring protons, it's the protons that are actually attached to that carbon. So if you look at, and of course now we would, so on this version, this OH, on this version, OH doesn't have a carbon, so it wouldn't show a peak. So when you look at the carbon peak, it only has 2 peaks. So then I could conveniently say 3 points for one, 3 points for the other. And then the number of neighbors for this peak, so this would have been this one right here. Would have been this one right here. It's got 1 hydrogen attached to it, so N is equal to 1. This one has 3 hydrogens attached to it, so you would have said N is equal to 3. And so on like that. So that's the way those were done. And then so then on the mechanism, all you did for the mechanism is it was just nucleophilic substitution. And I was just looking for addition, elimination. So here's the addition step. Here's the elimination step. There were 2 steps. It was a 12-point question. So 6 points for one, 6 points for the other. If you just gave me the final answer, you only got 6 points. But that was a pretty straightforward. So one was a Fischer esterification reaction where you had an alcohol adding on to the carboxylic acid. The other one was where you have an OH in replacing the halogen on the ethyl halide. So any questions about the way that your exams were graded or how the exams were done or anything like that? Okay, and I did tell you, you will get an MR spectrum and you'll get an IR spectrum on the test, on the long answers. So there it is, it showed up. We had almost the same thing on the quiz. I think people actually did better on the quiz than they did on the exam. It might have been because I wrote the quiz in a way that you could write almost anything, and I sort of had to give you points for it because I didn't specify that you had to give me the numbers for the integration. And I think that's the reason why people actually got better grades on the quiz, because I just sort of gave you points if you had almost anything written down. But I was looking for actual answers on the exam. Okay, so then let's continue with what we were. I'm hoping to mostly get over this carboxylic acid derivative chapter. We've already mostly gone over the major reaction of carboxylic acid derivatives. That was a nucleophilic substitution reaction. So we're just doing just that, nucleophilic substitution reactions. So we're back to carboxylic acid derivatives. This is chapter 22 in this textbook, but it's actually chapter 20 in your Libre text. So if you want to find where that is, it's in chapter 20. Okay, so I'm not going to go over the entire chapter because we've already covered all of the nucleophilic substitution reaction mechanism stuff. We'll just briefly cover that, but we didn't cover the nomenclature when we were doing the nucleophilic substitution on carboxylic acid derivatives before. So here we are, carboxylic acid derivative, carboxylic acid, acyl halide, and it says chloride, but really acyl halide, acid anhydride. We did not discuss acid anhydride earlier, so here it is. I kept saying that there is an acid anhydride when we were discussing the reaction, the nucleophilic substitution reaction mechanism chapter, and here it is showing up. So all you're doing there is you have a Z group where Z is some sort of electronegative atom that's attached to something else. And then here's our ester, and here is our amide. You could have, for the acid anhydride, which we have not discussed before, there are different types of acid anhydride. So you can have a symmetrical one where both sides are the same. You could have one that's mixed. So this has an acetate group on this side and a benzyl group on this, benzoic acid derivative on this side. You could have a cyclic one. For the amide, you can have a primary amide. That's where one R group is the actual carboxylic acid derivative part. And then you've got a secondary where you've got another R group on the amine, or it's actually an amide, but you've got another R group on there. And if you have 3 R groups, or you have 2 R groups and the original carboxylic acid derivative making up the 3rd R group, it is a tertiary amide. Okay, so those are the types of amides that you can get. I guess I could potentially put this on as a new multiple choice question for the final. But yeah, I kind of think that this is I'm not going to do any reactions on these or anything like that. I'm not going to ask you to name them or anything. But this is a gamma lactone. So this is alpha, beta, gamma, and you got the ester at the gamma position. This is a delta lactone. So this is alpha, beta, gamma, delta, and the ester is at the delta position. This is a beta lactam, alpha, beta. Penicillins are actually all beta lactams. Penicillins, all the penicillin derivatives are all beta lactams. This is a gamma lactam. And you see this one says lactone because it is an ester. This is a lactam because it's like an amide, so AM of the amide. And then this is a nitrile, so you've got R attached to the cyanide group. And then this you can sort of treat as if it is a carboxylic acid derivative. You can actually sort of treat it like an anhydride of a carboxylic acid derivative, because if you add water to a nitrile, a cyano group, you will actually generate a carboxylic acid. So this, you add water to it. That was one of the reactions that we had in the previous chapter. You add water to it, it will generate a carboxylic acid. So sometimes people do consider that to be a carboxylic acid. So this is, and once again, I did ask you for the most reactive and to the least reactive carboxylic acid derivative. We're adding on one more thing, the acid anhydride. So acid chloride, acid anhydride are similar in reactivity. They are the most reactive carboxylic acid derivative. And then we have carboxylic acids and esters that are similar in reactivity. And the least reactive carboxylic acid derivative is the amide. And why would you want to know that? Well, it's easy to go from here to anything that's less reactive. It's almost impossible to go from an amide to convert that to an ester, or to convert an amide to a acid chloride. That just is not going to happen. So you can go from a reactive to a less reactive, but almost impossible to go from a less reactive to a more reactive. So that's why this is important. Okay, so here's the naming. So what you do is you first, if you run across a carboxylic acid derivative, you first name the carboxylic acid that it's derived from. So in this case, I made up one where you have CH3, CH2, and then the carbonyl carbon. I drew that line and it sort of moved when I moved the molecule around a little bit. So this thing is basically a propanoic acid. Why is it propanoic and not, why isn't it ethanoic? Well, the carboxylic acid carbon counts as one of the carbons. So it's got 1, 2, 3 carbons in the carboxylic acid part of the acyl halide. So it's a propanoic acid. So this is derived from propanoic acid. This is derived from a propanoic acid. This is derived from an ethanoic acid. This is derived from a propanoic acid. This is derived from a propanoic acid. This is derived from a propanoic acid. So you're going to say propanoic acid, and then you remove things off of the ic acid. So you remove the ic acid, and then you call this a oil chloride or oil halide. So I would not bother with the carbonyl chloride. That's more of a common nomenclature thing. I would go with ill chloride, or usually it's an oil chloride, just because the name flows better if you put in that O there. So this is propanoil. It used to be propanoic acid. So it used to be propanoic acid. Used to be propanoic acid. So what you do is you remove the ic acid. And then you add on the ill chloride. So then it becomes propanoil, propanoil chloride. Because you just remove the ic acid and add it on the ending. This one is you're going to remove the ic ending, the ic acid ending, and you're going to write down anhydride. So this one is an unsymmetrical acid anhydride. So this side is propanoic acid. Like all the, I did all the names starting with propanoic acid. So then the other part is a ethanoic acid, acid. So then on the ethanoic acid, you also remove the ic acid. And then it becomes ethanoil, propanoil anhydride. And you do it alphabetically. So that's why the E comes before the P. But this is, you just remove the ic acid and say YL anhydride. And then on the propanoic part, you remove the ic acid and it becomes oil. So it then becomes ethanoil, propanoil anhydride. So the name is here. Okay, now for an ester, you got an alkyl group hanging off of the oxygen that makes the ester, the OR part of the ester. And then you've got the regular part that looks like a carboxylic acid. So the carboxylic acid part becomes, it's still propanoid. But it is propanoic acid, but for an ester, you remove the ic acid and add in ATE. So then it becomes propanoate. And then you have to name the part that is the alkyl attached to the oxygen, and you name it as alkyl. So there's 2 carbons here, so this is an ethane. Remove the E and add YL, so then it becomes ethyl propanoate. For the amide, you got the propane amide, so you remove the ic acid and add on amide. And then if you got an alkyl group hanging off of the amide nitrogen, you say N, and then you name the alkyl group. So if you had an ethyl group here, you'd say N-ethyl. In this case, we have an N-methyl, so we say N-methyl propane amide. So for the nitrile, you're just going to say propane. So you remove the ic acid, and then it's propane, propano, and then nitrile. So you just add on the ending nitrile. So I do realize that this is probably kind of complicated. Am I going to ask you to name something? What I might do is, this might be sort of more of a recognition kind of question that I could ask on the final. So I can give you a name and ask you, is this a good name? Or which of these names is an improper name for, this molecule? Something like that. That I could do. But I don't think I will give it to you as a separate nomenclature question where I give you the molecule and you have to name it from scratch, because it is a lot of, we're going through like 5 different functional groups in one sitting and on a very short timeline. So I don't think and we don't have enough practice. I haven't given you any homework on this. I'm not anticipating giving you homework on this. We don't have time for that. So I would say, that's pretty much it. Okay, so then here's another version of the thing. This is more like common nomenclature because, the name for benzoic acid, if you named it as a following the IUPAC nomenclature names, you wouldn't call it benzoic acid, although people usually just call it benzoic acid because it's almost the common nomenclature became IUPAC. But this is based off of benzoic acid, so then you remove ic acid, and then you say benzoyl chloride, benzoic anhydride. This one's symmetrical, so you can just say benzoic anhydride. Ethyl benzoic, this is still the ethyl group, and then this is the benzoic acid. Remove the ic acid, add ATE, becomes benzoate. N-methylbenzene, amide, you add on the amide, remove the ic acid and add amide. Benzonitrile, remove the ic acid, add nitrile. So there you have some more examples. This actually is the one that was actually in the textbook. I don't think I'm not sure if it's in the textbook of the Liber text, but it was on the textbook for the edition of the textbook that I got this from. Okay, so for the acid anhydride, here's an example. I wouldn't worry about anything that deals with common nomenclature. I wouldn't worry about those at all because I'm not having people memorize a bazillion different common nomenclature things. But this is just plain old, you name the, if you were naming a carboxylic acid, you would say, oh, okay, so you got 1, 2, 3, 4 carbons. So this is basically a butanoic acid. And hanging off of the butanoic acid, you got a methyl group. And the methyl group is not at the carbonyl carbon, it's at the 2 position. So it's 2-methyl-butanoic acid. And then you remove the ic acid, and then you add on oil chloride. So it becomes, it's not really oil chloride. You're actually only adding YL chloride because you just leave the O. So it's, here, this is what you're doing. So you got 2-methyl-butanoic acid. So that would be if you had this carboxylic acid. So the name of that carboxylic acid would be 2-methyl-butanoic acid. And then you remove the OH and replace it by Cl, and then you remove the ic acid, and then you add on YL chloride. So it's basically all based off of the carboxylic acid name. Okay, so when you do the acid anhydrides, those are actually a dehydration of 2 carboxylic acids. So here's one carboxylic acid, here's another carboxylic acid. You remove water, you take the OH off of one, you take the hydrogen off of the other, and then this oxygen connects the 2 carboxylic acids, and then you end up with the anhydride. So that's how you get the anhydride. You dehydrate 2 carboxylic acids to generate the anhydride. I wouldn't worry about the nomenclature for nitriles. Nobody knows nomenclatures for nitriles. No organic chemist knows the nomenclature for nitriles. But you do actually count the carbon of the nitrile as carbon 1, just like you count the carbon of the carboxylic acid as carbon 1. Okay, so the very common reaction that all of your carboxylic acid derivatives do, which we've already discussed, is nucleophilic substitution of the carboxylic acid derivative. So we're going to do a nucleophilic substitution. So the Z gets replaced by a nucleophile. So, you had a gazillion reactions in the previous chapter. We're doing a gazillion more in this chapter. So you come in with a nucleophile, you end up with this sp3 hybridized carbon like that with a negative charge on the oxygen. The original Z group drops off and you end up with the nucleophilic substitution reaction. We already, that reaction mechanism has already been done on a previous test. But I could put it on there again. I just replace, I just put a different nucleophile on there, and then it becomes a totally different reaction mechanism. Because even the aldol is basically, I just changed the nucleophile. You just have a very large nucleophile, and it's basically nucleophilic substitution reaction mechanism. So once again, this is least reactive, this is most reactive. So you can very easily go from most reactive to any of the least reactive things. You cannot go backwards from the least reactive and convert it to something that is more reactive than the least reactive thing that you got there. Okay, nucleophilic substitution reaction mechanism. We already know how that works. So you've got the generalized formula for a carboxylic acid derivative where you got a Z there. Z could be anything, except that we have to keep in mind that it has to be more reactive than the thing that you're generating, otherwise the reaction will not go. So all of these reactions would go if this Z was a Cl. All of these reactions would go. So here's your addition of the nucleophile, this as the nucleophile, this as the nucleophile, this as the nucleophile, this as the nucleophile, and then you end up with acid anhydride, carboxylic acid, ester, amide, So you've already done this reaction before, so I don't think this is anything new that you have to learn, because it should be, you're just changing what's the nucleophile. You just have to keep the nucleophile where the NU was when you were doing the generalized reaction, and then you should be fine. Okay, so here's the acid chloride reaction. So here it comes with the acid anhydride. Acid chloride is slightly more reactive than acid anhydride, so you can do this. So here's the acid anhydride that's going to go in. Here's the chloride that's going to drop off. So that's a Z. You end up with the sp3 hybridized nucleophilic addition part of nucleophilic substitution. And then you do the nucleophilic elimination part of nucleophilic substitution, and you end up with the acid anhydride. So the only thing here that's complicated is that you have a large nucleophile. Other than for it being a large nucleophile, it's exactly the same reaction mechanism that you already did, and everybody did very well on the last test. It's the same mechanism. I just have a slightly larger nucleophile. So as long as you don't freak out that the nucleophile looks so big and has like things hanging off of it, you should be fine. And how do you know what part of the nucleophile reacts? It's the thing that has a heteroatom. It's not the heteroatom that's the oxygen. It's the heteroatom that's got most likely a negative charge on it that's going to react. It's not going to react with the R group. It's not going to react with the carbonyl. The nucleophile, this is the nucleophile. There's the nucleophile. Where's the nucleophile in your water? The oxygen is the nucleophile. So that's the part that's going to attach the carbonyl carbon. So if you just know that, then you already know all these reactions that we can do in this chapter. We've actually done some of these reactions in our previous chapter. So this is not something new, it's almost reviewed. Okay, and once again, you could take some other nucleophile and replace something big. So this entire thing can drop off and you replace it with some other nucleophile. That can happen. This is a very well-known reaction. We did this when we were doing our banana oil thing. So this is a carboxylic acid with an alcohol, and it's known as a Fischer esterification reaction. It's a totally reversible reaction. To make it go forward, you can either remove water out of it, or you can remove one of the products out of it. You can have lots of excess of the reactant, but it's a totally reversible reaction. It is a very well-known reaction named Fischer esterification. So all you're doing for that is you take a carboxylic acid and replace it by an alcohol. So there's the mechanism for that. And you can also go backwards, so you can replace the ester, the OR of the ester, with a water molecule. And that really is about the end of the chapter. So there's a little bit of stuff about lipids and fat and soap formation and stuff like that. But I think most of that is like, here's a little thing about beta-lactam antibiotics. So this is penicillin, one of the structures of one of the derivatives of penicillin. It has the beta-lactam. So that's all. And the beta-lactam actually does a nucleophilic substitution reaction in your body to kill the bacteria. I thought that was kind of interesting, but I'm not going to put that on the test. A lot of this chapter will not be on the test, but I would pay attention to the nucleophilic substitution. Don't get freaked out by the size of the nucleophile. Recognize what part of the nucleophile is attacking your carbonyl carbon, and then you should be fine. So the idea here is, don't just sit there and try to memorize every single last detail of every single reaction that you see. If you understand, and here's the understanding, if you understand that all you're doing is you're replacing one nucleophile by another nucleophile, you recognize the part that's doing the nucleophilic part of that molecule that's acting as a nucleophile, you don't even have to know that reaction. I could make up a molecule that nobody has ever seen before, and you would know what to do. This is what I'm hoping for. And that's how, otherwise, there's just so many reactions. Who memorize? Okay, you didn't have to memorize it because you got it in a little equation shape, but who memorizes so many reactions? If you understand how things go, you don't have to memorize it. That's actually the end of this chapter. Let's see, this class is over at, I got 5 more minutes. Let me just see if I can squeeze in. And why am I squeezing in all this stuff? I would like to cover all the things that anybody who's taken organic chemistry as a sophomore should have seen. You might not, be really well versed on it, but you should have seen it. And we were running a little bit behind schedule, so I wanted to cover one last thing out of this chapter. Oh, come on here. Let me move this down. And we got one more. And I'm even calling it the short version. We skipped the electrophilic aromatic substitution reaction mechanism chapter because we were running a little bit behind schedule, so we skipped it. It is chapter 18 in my textbook. It's chapter 16 in LibreText, the one that you guys can access. So this is the electrophilic aromatic substitution reaction mechanism. And it's just the basic one little thing that you can look at, and then we're done. So we only have one more day left in the semester, and then it's the final exam. So one more day, what we'll do is we'll just try to do a review on that day. And if I don't finish what I would like to cover today on this, we'll cover it on Monday. Okay, so just one little thing out of this chapter that I want to cover. Okay, so here it is. This is the one little thing I would like you to learn out of this chapter. So there's a reaction called electrophilic aromatic substitution. Note it says substitution, meaning you're going to substitute something by another thing. So you got an aromatic ring here. This is a benzene molecule. Every carbon on that benzene molecule has a hydrogen attached to it. It's just highlighting one of the hydrogens with that little blue hydrogen there. You come in with an electrophile. You substitute the hydrogen by the electrophile. There it is, nucleophilic aromatic substitution reaction. That's all. Okay, so what do you get for the electrophile? Here they are. So you come in with, if you you can put it on your little equation sheet, but X2 FeX3, you replace it with X, halogen. You get HNO3 H2SO4, you replace it by NO2. You get SO3 H2SO4, you replace it by SO3H. You get an alkyl halide aluminum chloride, you replace it with the R group. You get this is a carboxylic acid, an acyl halide. So this is RCOOCl. They just wrote it on a single line. This AlCl3, you get the acyl halide, the carboxylic acid derivative part of the acyl halide attached to the benzene. So those are the electrophiles. So The electrophile is the halogen, the electrophile is NO2, the electrophile is SO3H, the electrophile is R, the electrophile is RCOO, oxygen, and it attaches at the carbon. So there it is. Those are all of the electrophilic aromatic substitution reactions. All you do is, you don't freak out that the electrophile looks like this, but you just stick it on there. Okay, so you've already done, this is pretty much the entire chapter. There is a little thing. Okay, I'll try not to do good. Okay, all right, we'll say end of class. I'll try. Yeah, Oh yeah, I was gonna do homework, but I noticed that I actually had not given, I don't actually have any homework for this class. You can just, and I know people have been doing this, I think you can just go ahead and submit as if you just say you submitted, and then you could, because I think, are any people lacking on homework points? Are any people needing to get homework points in order to combat some zeros from homework not being all there? Well, I mean, you have an excuse, so excused people are not in the group that needs to do the homework. If you were just missing homework, you can go ahead and submit it, and then it'll lessen the number of points that you will lose out of the homework if you just go ahead and submit it. But you have to do it by 11, otherwise you won't get the points. Okay, all right. So we'll do a review on Monday, and then we'll have the final, and then that'll wrap up the semester. Yep, I'm not changing the syllabus. The syllabus is the syllabus. So if you missed the test and you didn't want, and you don't have an excuse, you can drop one of the tests. You can drop, I think I said one quiz. I don't remember off the top of my head, but whatever I said on my syllabus, I will on. Yep. You don't have class today?
Any holiday, because we gave our presentations.
Oh, okay.
I was gonna say to do presentations, but
Yeah, that's why I asked Kessler if she got her, or they got her presentations.
nice.
People are expecting me to do something. They should tell me about it. I just decide I'm doing something behind my back.
Have a good day.
Yeah, same to you. Yeah. Yeah, I got the exam graded for the biochem too. I'll hand it out. I just have to find it in my other folder.